fucking puts my head on the ground.
I heard it's mostly rations.
She puts my head on the ground, sits on it, fucking grabs my underwear and shoves her heel through it. Gives me a wedgie.
Okay, let's study Chapter-6 today. So Chapter-6, we studied so far, we have a few of those equations. And most of the equation calculation is about this delta E. So we know delta E has the information about the interchange of the heat and work. So therefore, we can measure how much heat transferred, how much work was received or performed, and then we can calculate the delta E. And so even though we usually will not know like this E, so this E itself, if I want you to calculate for a given like material, for a given bottle of water, for example, calculate exactly how much internal energy in this bottle of water. That is a very difficult work. But we can calculate the change, which means delta E, for most of those chemical reactions and so on. So therefore, it's interesting to know if we can calculate or measure this delta E. Now, we talked about last week one instrument. So some of those people invented like one instrument called this kind of calorimeters. So you can see this calorie, standing for heat, and meter is some of those instruments. We can use some kind of instruments to measure like those heat. And so then in this instrument, what is really like innovative is they put those chemical reactions into a small like container. And that small container has a very small volume. So therefore the volume change in the process of the chemical reaction is negligible or ignored. And if we also ignore or neglect some other form of work, for example those electrical work, and so therefore we will have this W equals 0. And so then you know like if you W equals 0, that delta E will only equals Q. Right. For example, and if we put like some material in that little container, and in this example is about 1 gram of sucrose, which is a type of sugar, and so then you somehow like use those instruments and just switch or switch on the electrical current, and that can ignite or starting the chemical reaction. And so then the chemical reaction we talk about here is the combustion reaction, right? And so then combustion reaction is the typical exothermic reaction, which means release heat. And because of release heat, and that will make that calorimeter temperature increases because the calorimeter will receive the heat, and then temperature of the calorimeter change from 24.92 Celsius and increase to 28.33 Celsius. Alright, and so then according to the program, some other people also find out, use some other chemicals, and the heat capacity of that calorimeter, that means that whole thing together. You have some water inside, and you have the container, you have the insulation. So that is measured by someone else. Right. So then our purpose is to determine these delta E reactions. And then we know delta E reaction or delta E anything, it will equals, if we use the subscript, will be the Q reaction, and then plus the work of the reaction, how much work was the chemical reaction do or was it received, right? So in the last slide, we write that the delta E out. We don't have that subscript, which means you can refer to that delta E for anything. Maybe for a chemical reaction, maybe for a bottle of water. But once you have the program, if you calculate the delta E for the reaction, you can write everything as a reaction, which means the Q is for the reaction, and then the W is also for the reaction. Right, so according to our assumption, we have that bomb parameter, which means that W reaction equals 0 because that container, the volume is very small, so even though you have the volume change, but the volume change will be very small. Right, so therefore we will have this delta E reaction equals Q reaction. And we talk about to measure those heat release absorbed by the reaction. Reaction has those chemicals. You want to measure those chemicals temperature change by themselves. It's a little bit difficult. So what you measure like the kind of like the what happened, because of the chemical reaction, what influenced something else. That in this example, it will be the so-called calorimeter. So calorimeter, you can think about this calorimeter, that whole thing, everything together as our surrounding. So this equals surrounding. We talk about it in the first section. The whole universe divides into system and surrounding. And then this chemical reaction, and you can think about this as our system. Right? So now we know the universe will be only these two parts, and so then they will have the similar increases or decreases for the E, and then just opposite sign. So once we know that, these delta E reactions that can equals negative Q calorimeter. Because that's the only two parts, and according to our assumption, according to our technique, that will be the only two parts that has the energy interchange. Everything else is isolated very well. Alright, so then we also learn like pretty much from those data, from the temperature change, we have two formulas to calculate the Q, and both of them has delta T and delta T, but depending on what else we know, and we might use different either one of these two equations. Alright, so one equation is M, which is standing for mass, and times C of S, and then times delta T. That will give us the heat. The other one is capital C times delta T. Well, so then you know which transfer we use. You can just identify those by the unit. So this C of S will have the unit, typical unit for energy, and then typical unit for mass, then typical unit for the temperature. So this is one way to identify which formula we use. So then this, it will have the unit joule per Celsius, no grams. Alright, so then you read this question, and what it gives to us is about that C for the calorimeter. And we need to use either one of these two formulas to calculate this last number. Alright, and because the heat capacity for the calorimeter is given to you, and then you read this number given to you is a kilojoule per Celsius, and I write here typical unit for the energy is joule, but obviously you can use kilojoule or calories depending on like those two questions. Alright, so therefore, once we know like the information given to us is a heat capacity C, not a specific heat capacity C of S, so therefore we are going to use this equation to the calculation for the heat of the calorimeter, and you just use those numbers very straightforward, kind of easy. And so this part is our capital C. So according to this formula, you want to get the Q, you need this C, so C is given to us, so therefore we just put into the formula and that part. And then you have to figure out what is your delta T. Delta means change. Any change should be the final value minus the initial value. You talk about the delta T, which means the temperature change. You take that final temperature, so this is our final temperature, and this is our initial temperature, so therefore we have 28.33 Celsius. I even like, assuming we know that we don't need to convert into the temperature scales because that's already in Celsius. Minus 24.92 Celsius, so that will finish this problem, the calculation. I mean, finish this step of calculation. And it's very easy, so we just take 28.33 minus 24.92, and you get, so the delta T for this problem, you get 3.41 Celsius. So this number come up, it becomes like 3.41 degrees Celsius. And then you just multiply this onto the capital C, which is 4.90. Right, so let's multiply 4.9, and you get like, so you get 16.7. Now you will see the unit and the sign. See the unit, initially this guy has kJ over Celsius, and this only Celsius. So Celsius, this is on, I write here, but that means you still have this number here, okay? On the top. So if I use this equation here, so forget about the negative sign there, because we just, so if we calculate this is for the calorimeter, and just 4.90 kJ over Celsius, and then just multiply 3.41 Celsius. So I write on the slide, it looks like this is the, I don't think this is the fraction, so we just, right? Right. So you can see this Celsius and Celsius kind of out. So therefore what you get, this 16.7 Right now I only have the unit kilojoules, and you still have the negative sign, right? Because that's come from our that step, right? Now the problem is you have to read the question carefully. In the first few seconds, I think that's pretty much that's it. Just calculate what is the delta E for the system or for the surrounding as like one as one something. Now this question is you need to calculate. So right now this equals delta E reacting. Delta E reacting equals negative 16.7 kilojoule. Now the question asks you do a little bit more like than what we did in the first few seconds, which means you want to find out kilojoule per mole of sucrose. Now emphasize again. So right now this negative 16.7 kilojoule is not for 1 mole of sucrose. It's for how much sucrose as our system. It's for how much sucrose.
You have to convert it.
Yeah, the sucrose given to you.
1 gram.
About 1 gram of sucrose, right? So you can understand, so this much of heat released from that example of sucrose is from about 1 gram of sucrose. I said you have to read the question carefully. If the question asks you to figure out a kilojoule per mole of sucrose, and so what do? You assuming, or you understand, so this negative 16.7 kilojoule is just for that much gram of sucrose, or for that much mole of sucrose. You want to find out per mole of sucrose. You just find out in that 1 gram of sucrose how many mole. So if this is for that amount of mole, I say X mole, and then you find out what is that X mole in that 1 gram. And then you divide this number by that X mole, you will get per mole. So therefore, next step, so that's the new step in this section. You don't have to do that in the first few sections. You find out what is your Q, what is the W, and put them together, you find that delta E. Right. So now let me erase all those. So right now so far we find out delta E reaction equals negative 16.7 kilojoule. And this is for 1.010 gram of sucrose. So I just write abbreviation sucrose. So what do you do next? Convert this much gram of sucrose into moles. So therefore you will find out how many moles. So now you see that's so important, as I emphasized since the second chapter, to converting from gram to mole, and you have to know that very well. Use molar mass. Okay? So the molar mass here gives you, you have a 342.3 gram of sucrose, and I have 1 mole of sucrose. So gram of sucrose comes out. So therefore you get how much more of sucrose. Right. So 1.01 divided by 342.3. 1.01 divided by 342.3. 0.00295 more of sucrose. Right. So then you want to find this number. So what you do, you will just take that negative 16.7 kilojoules is the unit of the kilojoule. Right. Right now you don't have that per mole, or the mole in the denominator. So you just take that, divide by 0.00295 more of sucrose. Now we have the unit is what we want. So I probably include that part too, more sucrose. Right, so 16.7 divided by the number we just get, and you get negative 5659.8 kilojoule. So I keep like too many the single figures, and obviously you can just see this is become let's say 3 single figures. So that's what we started in paper 1. So that equals negative 5.66. So I want to keep 3 single figures. So I have to use scientific notation. Because otherwise I will write 5660, right? Because I want to run into this 5, that will give me 3 single figures. But if I write something like that, that's, if I put a point on, that give me 4 SF. If I don't use a point, then we have those ambiguity, not very clear. So therefore you use 566, then times 10 to the 43. And then your unit is still this part. And then I don't have space to write that. Still kilojoule per mole of sucrose. Alright, so summarize what we did in this example is we use one of those equations, find out what is that heat of the calorimeter. Then we use the first law, we switch the sign and change that into the heat of that chemical reaction. So that's the first part. The second part of what we did is find out the mole of the sucrose, then divide the number we get from the first part by the mole of the sucrose, and finish the question and get the number, how much kilojoule of energy that released or absorbed by the reaction per mole of some of those reactants. Okay, any questions? Okay, very good. So I think that, yeah, so that's, you can see from the slide of the book. So you have that negative 5.66 times 10 to the positive 3 kilojoule per mole of that C12H22O11, which means sucrose. All right, so let's do a practice. So this practice is very similar as the example. You needed more mass, so you probably just find that sooner or later. So follow the example, follow that two parts in the example. First find out that heat, right, of the calorimeter. And obviously we have to use our assumption with assuming that work is 0. You first have to use that one of those two equations I write on the board, right? Find out the Q parameters. Okay, so that is that. Don't divide by the yeah, the amount of moles, right? Okay. Yeah, that's and then just don't forget to switch the sign, so you have that delta E equal to negative Q. Good, good. So it seems, and that's what I want you to do. Just you can referring back, look back at the example, and then do the practice. So this will pretty much matching pretty good. What do you find out? Yeah, so first use one of the two equations. You probably want to use the second equation. Right? Yeah, so that number looks good. Negative 17. Yeah. Then, yep. More, you can find more very easy. You have 2.55 grams of something, right? So you find out the heat. Very good, very good. Yeah. And that number is right. It's a negative that, and then divided by 4. Yeah. You can see. Okay, so I see that number is pretty good. Yeah. All right, any questions? Very similar as the example, okay? And you first use the equation delta E reaction equals negative Q. Let's just use like abbreviation calorimeter. Right? And that becomes negative, let me write that C times delta T. And then you have one more step, negative 5.73 kilojoule over Celsius. And I just find out what is delta T. So delta T will equals TF minus TI. And that will equal 38.13 minus 25.87, and that give you 38.13 minus 25.87 and 12.26 Celsius. So you will put here 12.26 and the unit is Celsius. I can see the Celsius comes out, and I think most of you did pretty good. Times 5.73, you guess I think negative 70.2 if I just make it simple, keep it 3 as I have.
You're supposed to have the mass in there.
Huh?
2.5.
Okay, good. So now we have this. This is like what we usually do in the first phase section, right? So we know this is for. So this is the heat is for 2.550 gram of this guy C6H14. So this we call that is our let's see part one calculation. Right? So part one calculation you just use what you did before. Right? Now part two. For the part two, you want to find out. So in the first part, in the first step of part two, you find out more. Okay? I think in the lecture notes you did not do that. You just I think you just put them together. But if you want, I see what I did here. So you just starting like as usual 500 gram of C6H14 and then you have one more C6H14 divided by the molar mass, right? Molar mass of C6H14. You take 6 times 12.01. Anyone get the number? 6 times 12.01 plus 14 times 1.01. So I get 86.2 gram. Right? And this is C6H14. So that's that part. This step is our really like the technique we use many times. You have the gram divided by the molar mass, you get how much more. Right? So 2.55 divided by 86.2, 0.02296 more of this. Now this is the first step of part 2. So once you find out more, right? So now you just divide. Okay? So what you do, you will take that 70. So take this number here, right? Take that number here. So let me. Okay. So for the second part, so for the second step of the second part, you just take that number you get it from the first part, divide by this number. That is more in 2.55 gram. Right, so this is divide, right? 0.0296, right? And this is more. Right? So let me just finish this calculation, and this was our second part. So, you already know, like that's very straightforward. Right. So you have this two number divide, and that will give you. So let me just take 70.2 divided by 0.0296. So you get negative, so you have a negative 2373 kilojoule on top, because you divide by mole, so therefore per mole. Right? So the number divide out, but you cannot divide the unit out yet. Right? Okay, so then you want to put this in the scientific notation with 3SF, and that becomes C. Okay, any questions? Any questions? You know which number you get it from where? Alright, good. That's pretty good. Okay, now try this one. Right? So this one, read the question and see what you want to find out. What it gives you. What do you find? Right. First, use that switch is pretty much because that's one positive problem maybe because that's two parts of the universe. Yeah, you have to change into kilojoules by itself. Right? So let let's see what you do. You have that 3.9 10 to the power 3900, and so then how can you cancel out the more? You don't want that anymore. You have to divide by you have to multiply by the more. Right?
Yeah.
So that's the more. What is this number? Is it more mass? Well, more mass. Okay, so then if you want to use a more mass here, and that means in this way.
Let's use 1.5 divided 1.55 over 19.1%.
Yeah, so like that. Yeah. So yeah.
Okay.
Right.
Somewhere right here. I think that's right.
What that means? 3910. That means divide, right? Not divide. That means that you will put that number on the top. So 1.55. 1.55 grams, and then you divide by this number, so gram comes out, and then you know that means you purchase right, not like in that format, but you need to understand. Okay? So you have this one by yourself, then they have to kill you over one more, right? And if you multiply by how much more, you will get how much joule from that much more.
Oh.
Yeah, maybe simply pick that up. There you go.
Okay. Thank you.
What do you get?
I got A.
You get A, not E.
No?
Oh, interesting. What do we get?
What was it?
A or E? What do you get?
Alpha.
You get A? What do you get? A or E? A? You get A, probably that's, the number is the same number, just sign number different. Don't forget, you need to change the sign. The question is you want to find out the heat capacity of the bomb calorimeter. So not a specific heat capacity, just heat capacity. So therefore you just want to find out the C. Right? You don't want to find out the C, and you want to use one of those equations about the heat. So you just write everything in terms of this calorimeter. So you write that it's Q calorimeter. I just use CAL for the calorimeter, right? And that equals C calorimeter times delta T, right? This is our question mark. That is our utmost question mark. Right? To find this, you have this equation, have that. Right? So therefore, think about use this equation. And our utmost, our final purpose is to find out this number. So therefore, you have to think about how can I get this number, how can I get that number. Let's do something easy first. Delta T is easy. That gives you and tell you the calorimeter, the temperature change. So yes, 32.57 minus 23.12. $32.57 minus 23.12, 9.45 Celsius. Now, a little difficult to find this guy out, right? You always think about, in those programs, two parts of the universe, and one you call that system. that means you have that system and surrounding. I use abbreviation. You can just call either your system, so you decide. So you can call this parameter. You can also call this our surrounding. So then our reaction will become your equals the system. So don't confuse by those names. You just always keep in mind there's only two parts in the universe. System, surrounding. Then your system kind of like, what is the person's last name? You just give them a specific last name. And then the surrounding will be your first name. Then you give them a specific first name. So what is that person's first name? Right? So the system and surrounding is kind of like two templates. And you can just fill your template with those particular or explicit examples. Alright, so that will remind you, okay? So this parameter is our surrounding, and our chemical reaction is our system. And you will have this Q parameter equals negative Q reactions. But in general, there will be a larger picture. That means you don't have only the Q, you will also have that. Remember what we did in one problem? So we gradually narrow down into this, but you're starting from that larger picture from this picture, delta E. Right? So now, because we don't have a work, so delta E just become Q. So you are given this delta E, and if you want to write, you will see delta E reaction equals Q reaction plus W reaction. Because you are using those kind of parameters, your volume change is negligible, so no work. So no work, that means you don't have W, so that disappears. And then you can use this number into those kind of equations, not directly. Because those equations, like those C times delta T, C times M times CS times delta T, is only about a height. And obviously, if you don't have like a work, you can use the height by itself. Right? Right. So we have this equation now, right? And so then the problem is how you find out this guy. You forget about the sign yet. How you find this guy? Right. So let me write I continue to write. So if I keep this sign, okay, so that will become delta E reaction. Now delta E reaction, but that's a little confusing because this number give you delta E reaction is given to you like negative this number than kilojoule per mole. What we need here is not per mole, for whatever mole that make that temperature change of the calorimeter from that to that. So you have to figure out from this number, this is per mole. So whatever mole in there, that's 1.55 gram. And so then use this as a conversion fraction, that is for 1 mole. So you know that those are typical conversions. And if you know how much mole, you can just do some conversions. Let me erase it also, that's kind of very messy. So what you want is to find out first. So then what I said is something like this. This delta E reaction for equals Q reaction because W equals 0. Now next you will find out what is really the Q reaction. Okay. Q reaction, this is the per mole. So if I convert this into moles, I will do something here, 1.55 gram. And then at usual, your usual technique, like use mole mass. So this 1 mole, this toluene C7H8. And what is the mole mass of C7H8? Do you have a number? 92.15 gram of C7H8. Okay, thank you. And this, as we talked about before, so those are the so-called conversion fraction. So this conversion fraction is from the molar mass. So what we are doing here is use the molar mass, first convert this 1.55 gram of toluene, which is C7H8, into the moles. 1.55 divided by 92.15. So get 0.0168 mole. Right? Yeah. Now you will see those kind of information from now on. So many times. Those are typical information. So I give you those chemical reactions that will have some of those heat. Maybe delta E in this section, and later on you will see those become delta H. So delta H is a little different information called the enthalpy. Delta E is about the internal energy, but the internal energy has some of those limitations because you want to use the internal energy directly, you have to use those kind of calorimeters, which is kind of not convenient to use in chemistry lab. What you usually use, just take like 2 of those cups and you don't have to like really put it into a small container. You can open to the air. So you do the measurement, very similar, you do the measurement for that one. But what I want to tell you, what I want to remind you is the unit it gives you is a kilojoule, like per moles or something like that, okay? Right? And maybe a kilojoule per 2 moles, depend on the information. Okay? Right. So you go back to the problem, you will see that. So Q reactions, so if I write 0.0168 more here, okay, and that one also become a conversion fraction, negative 3.91 times 10 to the positive 3 kilojoule, and here is also per mole, right? So there the per mole is kind of omitted, per mole what? But by your intuitive understanding, that means it's per mole of toluene. So even though there's not per mole of toluene, the tariff is for toluene, so therefore it's also per mole of toluene. So if I add, that means TOL standing for toluene. And here is also, obviously this means TOL is toluene. And here is also TOL toluene. Right? Toluene. Right. So you get some of those numbers. I think you should be able to see the answers now, right? So that becomes 0.0168 times 3910, and you get negative 65.7 kilojoule. Now you don't have like per mole, because the mole kind of out, right? So, but this number is still Q, we call that a Q what? Q reaction. So this look like precise because this tell you the heat released. We know it's released because we have this negative sign. Okay? By this amount of gram of toluene, and in those kind of combustion reactions, in those kind of parameters. Any questions?
What was the answer, A?
The answer is A. Yeah. So then, so this will become a negative Q calorimeter. Okay? See what I write here? Before I write this one, that's just you get the number from that. Okay? Now this equation, so the last equation, this last equal sign I put here, it is because we have the two parts of the universe. You can omit in this part, and then you know that Q in one part, the other Q is the other part. So that 2Q, if you don't have work, that means you will have the same magnitude and opposite sign. You see that equation simply comes from this. Q reaction equals negative Q calorimeter. You will use that many times. Right. So if you find out that Q reaction is negative this much, understand? So then you find out, when we did find out that Q reaction is negative 65.7 kilojoule from 1.55 gram of toluene. Now that will tell you that reaction releases that amount of heat. Now release that amount of heat that goes where? It goes into the calorimeter. What's the question?
So that's answer is negative 65.7. How is it A?
Okay, see there. See this one? So that negative 65 kilojoule is for this one.
Okay.
What does that mean? That means reaction. Right? That's a reaction. Rxn is chemistry sometimes like they become so this Rxn equals reaction. Right? You get those numbers for the reaction, but the problem is for the calorimeter. That's I said that's only two parts in the universe now. The chemical reaction and the calorimeter. So either one will receive the heat or release the heat. And they just opposite sign. No matter who release or who like absorb, that's opposite sign.
Okay, so it's the opposite sign, then it should be.
Okay, now you have this. Now this for the reaction, if the heat for the reaction is negative, because opposite sign, and the other part is what? Calorimeter, right? If the heat for the reaction is negative, and then this heat for the calorimeter will be positive because of opposite sign. Why is that difficult to understand?
If it's only the opposite side, it should be 65.7, not 6.96.
Oh, you confused. Yeah, 65, probably positive 65. Right? Probably positive 65 for the calorimeter.
Does it mean like negative Q means that?
Okay, no, let me, again, because I know that because I messed it with, let me just clean all those out. So what we find out now is right now is Q reaction equals negative 16.7 kilojoule, right? Oh, that's very confusing. Negative 60.5.
65.7. Negative 65.
do it again. Q reaction equals negative 65 on 7 kilojoules. So I have very good memory about the last question. So now again, this is Q reaction. Right? So we figure out if you take like 1.55 gram of toluene and do the combustion reaction, it will release this amount of heat. Right? So we kind of insulate, or we kind of isolate. So we only have that two parts. So we have that reaction plus that colorimeter. This colorimeter I'm going to use, so I will just simply call that CEL. Right? So now your universe becomes very simple. Only these two parts. Right? So because you can see this, you put like very good insulators like that, right? So all the heat released by the chemical reactions, it will go into the colorimeters and nothing else. So these are the insulators, kind of like insulators. And then they tell you, this will tell you if you don't have a work, so you only consider Q. So Q is a heat. So Q is a heat, right? And in general, you have to use both heat and work, but we kind of ignore the work. Right? We ignore the work. So therefore, we will have that Q reaction is about the heat from the reaction or go into the reaction. That will equals just opposite sign of the heat of the colorimeter. Right. Now let's say you can write either one. Right? So you have this number now, right? And just substitute this number here. So let's say we have this number for this guy. So what you do, you still have this negative Q colorimeter on this side. Now you have this negative 65.7 on the other side. Because you can just, if you don't have a number, you just call that a Q reaction. But you have a number, so why you want to always call some name? Just give some number. Your number is negative 65.7. And so then you have this negative here. So you have this negative here, that becomes positive. And then that's what solve the problem, right? Because once you have this, let's see, so therefore from this, so we get Q colorimeter equals 65.7 kilojoules. The next step is using one of this equation to find out this, I think this guy, right? So once you have this step, and you will see from this information, but that depends on this, how you calculate this delta t from these two numbers. If you do the opposite, then you will get back into a negative number from the delta t. So sometimes if you make like twice mistake, you are kind of out. If you forget to change the sign, you get a negative. Then you get a negative from delta t. Then you also get a positive for the C. Right. So I think that's for this problem. So as I said, for many of the chemical reactions, okay. So the last one is you have that. So you have that Q colorimeter now is 65.7 kilojoules right now, right? I remember that 65.7 kilojoules now. So then, let's say you also have an equation. So whenever we have a Q, you think about those equations, right? So you have an equation that Q, let's say colorimeter, that equals C calorimeter times delta T calorimeter. Now here I don't have all those names in it, but probably if I put a Q calorimeter here, so I forget, I should also put a here calorimeter and here also calorimeter, right? So now again, if you like really some kind of very like naive, well, not naive, the beginning of the science class, you have this equation, and now you also have that number, so you just substitute it. So you have this Q calorimeter here, and you have that number, so you just replace this by the number. And you can calculate what is your delta T, so therefore you can also replace this by the number. And only variable you don't know is this C calorimeter, and you just divide this number out. Alright, so let's do that. And we have this 65.7 kilojoule, and we can write this CL because we don't know the number. And our delta T, so we will find out what is our delta T, right? What do you find out about delta T? 9.45. 9.45. Yeah. So there we go. So this has a Celsius, and you want to get this number by yourself, so therefore you have to divide the 9.45 Celsius out and divide the 9.45 Celsius out. And then here both of them cancel out. The number, the unit cancel out, so you get this C like calorimeter. And then here you just divide. Okay. And after divide, I think you get 6 something, right? And the unit is really straightforward. So that's what it is. So that's why you just take. Right. So then let's see, like as I said, we have one section about measure those heat. Use this kind of instrument. You can see those kind of instrument. It's not common to use in a chemistry lab. In a chemistry lab, like you are just take some solutions and put them together, and the measurement. So therefore, typically in the chemical reaction in a lab, you just use those kind of calorimeters. And you use like those, you see like there's 2 cups here because you want to do a better insulate. So a similar instrument like this, that will tell us, and we like our universe becomes simple again. Okay? So inside this cup we have the chemical reaction, that is one part. Then we have those solutions, so that's the other part. Now the problem is, if you use this, and you measure those Q, right? You measure the Q, which is about heat. And then from the last few programs, you do like a few steps, right? And you find out those informations for the chemical reactions. So you use a very fancy instrument, and you do some calculations, you find out the delta E for the reactions. Right? The last CRE is kind of opposite. So I give you those information, and you find out that heat capacity. That's not usual. I mean, the main purpose of this is kind of like you have those heat, and then from the heat, blah blah, you can find out what is that. Now here, the similar like comparison. If you want to, you can also measure like those temperature change for those kind of calorimeters, and then that means you can also measure the heat. Now because here you have this container, even though the container looks like clothes, so we use all those like tedious stuff. You can see this. A cork lid or those kind of carb is very good of like insulating those heat, but they are not really like really sealed like to insulating those materials. So you can see like this, for example, this thermometers are stuck into the lid, and then this a glass like a steering bar stuck into the lid, and obviously there will be some of those leaking, some of those right. So you can the air can goes in even the lid. It's not easy to isolate to produce a kind of like a vacuum. Really, there is no matter can like easily change. Right. So therefore here and here you're like your volume looks like the volume for your container is like is fixed, but your chemical reaction volume, if it produces gas, obviously it will not be fixed. Your gas can escape. Okay? Or vice versa. If your chemical reaction needs gas, gas can get in. Right? So your volume is not fixed here. And if you measure those heat, then let's see what we measure. But even though like the internal energy make our common sense, because everybody like to know like energy is important. So you want to know like how much energy like in something, what is the total energy. Okay. Now next we introduce one concept is not really that common sense. Is solely because totally because we measure those heat at the calorimeter on the right. So we measure the heat from the calorimeter on the right, and you also want to like find out what is really measured. Does that really make like a sense or is have any connection to our daily life? So even though our daily life most of the time concerned with energy, but depend on what you think, and so some of those energy from the chemical reactions is like kind of those only the heat, and then that's like even though the heat that work is only the energy involved in some of those most common chemical reaction conditions. So then why not? So we will define something that can help us calculate or use it. Alright. So then one scientist come up with an idea called, he defined a new quantity called enthalpy. And enthalpy, according to like the definition, has this format. So this H, let me just write here, common enthalpy has the notation H. And before we know that internal energy common is E. Right? Internal energy common is E. And you can measure the change of the internal energy E, delta E, use that calorimeter by measuring the heat absorbed or released of the calorimeter. But you can measure this change of this H from the simple calorimeter. And so then let's see like why that is true. So this is the definition. So this is the definition. So people just call that H. And you can see what is in H. H equals E. E is the internal energy plus P. P is the pressure times weight. And E we know is a state function, and pressure volume is also state function. So when you have a function is a state function, so therefore H is also a state function. So let's see like what will be this delta E like standing for. Let's review what is our delta E. Delta E equals what? Yeah, Q. I'm going to forget what you said. Q plus W. I don't like have any. I did not put any like notation. I did not say whether this is for our whether this is for our safety or surrounding. If I don't put those on as a subscript here, if I don't put like the S, Y, S here, or S, U, R, R here, which means those equations can be for either one. Just be consistent. If I put a subscript here, delta E, S, Y, S, then everything will be S, Y, S. If I put delta E, S, U, R, R, then everything here, the Q will be S, U, R, R, and then W will be S, U, R, R. Alright, so let's keep that more general, a generic equation. That can be for either one. Right? And so that's what we know from the previous sections. Right? And then you just use your like common sense and find out what is delta H from the definition. So if you know like H equals E plus PV, right? So that tells us the change of H, it will equals the change of E plus the change of PV. Right? When you have like adding together equals something, then the change will equals adding together. So it will equals delta E plus delta PV. But let's be more like clear. Here we're referring to like the chain of PV together. We call that delta PV. Right. So then, from the last equation, you already know. So this delta E, the first one is Q plus W. So therefore, why don't you just replace delta E by Q plus W? And then let's keep this still just repeating one more step, so that we call that still delta PV. Alright, now just keep writing. So you still have that QW, so you don't worry about that. Just rewrite that. What do you mean by delta PV? Delta PV means the change of PV. Right? Any change will be the final minus what? Minus initial. So what you will rewrite, so this guy become PF, VF minus PI and VI. And that's straightforward again by the definition. The delta PV should equals the final PV minus initial PV. Right? Now this, right now you don't have any like limitation on your process. We talk about process because we talk about delta. Right? So delta means you have the final, the initial. So now let's draw a line here. Okay? So I'm going to insert some of those limitations. So we'll see for those constant pressure processes. Right? I think that's straightforward. When we see constant pressure, which means the pressure is not changing. If the pressure is not changing, and so then what happened to those PF and PI? Well, let's see. Let's just. You mean they are equal? Constant. Constant means they are not changing. That means your initial pressure equals the final pressure. That makes sense? The same number. You can call that PF equal to PI. Right? And you can also make it similar because PF equal to PI is similar to that P. Yeah, so that's just one pressure. Just one pressure. Right. So then keep writing. So out of this line, okay, So we have some of those not very general now. That means not for all the process, not for all the chemical reaction, only for the chemical reaction that has a constant pressure, means pressure that on the chemical reaction are constant. And so therefore you probably call that give that a special name. So you still call that Q, but you just use, because we have a special process, we have that constant pressure, you just call that QP. Right? Call that QP. And I think the book did not give that a special name, but you can give that W also special name for that WP. Right? Alright, now you can just replace this PF become P. Right? PI become P. Right? So just replace them, both of them by P. So we have P VF minus P and VI. Follow me? Alright, so you keep writing, you will see this QP plus WP. What you can do next, you need to review another very important formula. Right? Now before that, you do some of those algebra. So here you have this is we call them like the term. Right? So you have the first term has a P, the second term has a P. So just pull the P out. So just write a P in the front. And then you have that VF minus VI. What do you call VF minus VI? W. Right. So now let's go to the reverse. So we still have this delta H. So what are we talking about delta H, right? About delta H. So let me erase some of those. So we have a little more room. So right now let's keep writing. So from this line, and I will write there. So delta H equals QP plus WP and plus P times delta V. That's very straightforward, right? So I just copy this QP here, and then I will copy this WP here, and I will just copy the P here. I just rewrite VF minus VI as delta V. Right? So then I want you to review like one important equation. Right? Remember those the so-called P V work? Do you remember like my formula for the P V work? P V work, we still call the W. Remember there is the equation like in my section? W equals what? Yep, negative P times the volume change delta V. Now in that equation, you also have that, so there's a P in the front, that's also because we're assuming our pressure is constant. Right, so what we want to see is you still have this QP, right? Now because of this, right, so this WP become what? Yeah, become negative P times delta V. Okay, then you still have this last term. The last term still what? Yeah, so that writing is not very good. So but you understand that P times delta V. Now that becomes simple, right? So right now we have this delta H has three terms. We have this QP, then this negative P times delta V, then this positive P times delta V. And this one we what? We cancel out. Right? So therefore, our final conclusion, after this line, so that means after this line, And what this line has a very important assumption. What this line about? What is this line about? For some of those, not a very general process, for what kind of process? For process that has a constant pressure. Right, so therefore, we come up with our conclusion. This equation is true for any process, for any kind of process, no matter your constant pressure, constant temperature, constant volume, just that is true.
Which one?
The one on your circle, the delta E. But this is the first law of thermodynamics. So no matter what kind of process, you know that your energy should be conserved. Now because we define, so we have this new quantity. New quantity, we call it H. We call that H. And you can also measure the delta H. Measure the delta H. But in general, delta H, so this is also true for every process, for any process, even up to this step. So here, right? So this one here is true for any process for delta H. But it's like what is, I mean, you define some of the quantity, sometimes it's purely for those fundamental studies, but sometimes you want to see like what is your connection to the to our daily life. Right? So then, as I said, our daily life is a little easier to measure those chemical reactions, open to the air, which means the volume can change, but the pressure is not changing, not really changing. The pressure, when you have those like the calorimeters, you know that you are not sealing very well with those lead, right? So therefore, the air, if the chemical reaction produces gas, the gas can escape. If the chemical reaction needs gas, the gas can get in. So it's kind of open to the atmosphere. So therefore, what pressure those chemical reactions is really under those air pressure. And air pressure pretty much constant. Right? So therefore, we insert this limitation. We say, let's see like what happens to our delta H if your process has those pressure that is constant. Then we say like after we have that assumption, and what we find out is delta H equals Q of T. Right? Well, just tell you. You compare those, and you can like what we saw before is that Q, delta E equal to Q, and in few of those programs you probably put that delta E equals Q of V, which means constant volume. Right? Yeah, so yeah, there's two important quantities. One important quantity is like the internal energy, and another important quantity. Well, what is really important is the interaction of, the influence of the chemical reaction with energy. So either the energy released by the chemical reaction, or the energy absorbed by the chemical reaction, how much absorbed, how much released. That is really like important to us. We always worry about what is our fuel efficiency, so that when you drive a car, how many gallons and how many miles. So those are all about chemical reaction, energy, and heat. So you want to get those, for example, you want to get those chemical reaction heat, and you can measure them and put them in a table so that everybody can use it. And then if you measure those guys at a constant volume, that's really not the typical chemical reaction happening in our daily life. You drive a car, even though the car has those, you can assume those chemical reaction is under the constant pressure. That it's not precise by inside. Most of the time, the chemical reaction is just the pressure is constant. So you can use those information, and even though this H initially does not make too much sense. But if every chemical reaction or most of the chemical reaction having under those kind of conditions, so why not? Why just summarize all those information for most of the chemical reaction that has those delta H, and then you can just use those delta H for some chemical reaction, calculating those delta H for some new chemical reactions, and we know those delta H is connected to the heat, and heat is important for us. Right. So that is why we introduced this very tedious concept about the enthalpy. Right. So therefore, you can measure. You will have a very good understanding why you measure the delta H. Okay? Because you measure the delta H, okay, that will tell you what is the heat absorbed or released by the chemical reaction or some of the physical process, okay, under the constant pressure process. You are very annoying why you emphasize the constant pressure process. But once you realize those constant pressure process is very typical, so that means it becomes like trivial. So most of the chemical reaction is a constant pressure process. Right? So really delta H is measured those heat absorbed released for the process for those under the constant pressure process. So then you will see like very often those kind of definitions like delta H is negative, which means the process release heat. Right? So you saw those previously those chemical reaction give you those delta E, even though precisely we don't use delta E to say that is endo or exo, we just use delta H. Right. So make some good memories. So when you have a negative delta H, which means the process for that delta H, and maybe a chemical reaction, maybe a physical process. Chemical reaction like what we did in the chemistry lab, we take a power plant and burn it, and that's a chemical reaction. A physical process can be simply you observing like those moisture in the air condense into frost or condense into the morning dews. So those are simple physical process. But all the process, no matter they are chemical or physical, and you will have a delta H. So if your delta H is negative, which means that process releases heat, and then the name is called exothermic. And vice versa, if we have that delta H is positive, which means the process absorbs heat, that's called endo. Okay? Right, so that is the definition of endo and exo. So don't be confused. Okay? And so those exothermic reactions, and because it releases the heat, so your hand gets warm. It's not your hand releases the heat. Your hand actually receives the heat, and vice versa. If you hold a chemical reaction, okay, in your hand, and if that chemical reaction is negative, then your hand will feel warm, and vice versa. If you hold a chemical reaction, the chemical reaction is endo, which means the chemical reaction or the physical process absorb heat, and then your hand will have to supply the heat, so therefore your hand will feel cold. So like say if you have some of the common like knowledge, or you like pay attention to the process, identify each process is endo or exo, and also indicate the sign for each one of these. The first one is the sweat evaporating from the skin. That's considering that sweat is what we want to be referring to. So when that sweat evaporates, will that release heat or will that absorb heat? Think about sweat is kind of like water. Okay? So when water changes from liquid into what do you say? Liquid to gas, right? So when material changes from liquid to gas, and you absorb heat or you release heat. So those were those materials, they absorb heat in order to change from liquid into gas. What you can think about is in the liquid, they move in a little slower, so they have less kinetic energy, right? I think everything else is pretty much similar, and you have the similar chemical. Water is H2O. Right. So this it will be larger than 0, or we call that positive. Okay. And then positive delta H, which means is endothermic. Right, you get that. That's really good. Just think about what you're referring to. Okay, that's referring to here is about the sweat. And the second question about water freezing in a freezer. So we talk about the water. So that delta H, and whether they are smaller than 0 or larger than 0, smaller than 0, right? And that means they are negative. They are exothermic. And so water freezing might not spontaneous. That means the heat will not spontaneously come out from the water and then become ice, depending on the condition. And you probably have to, use. That's why you have to use a freezer to take the heat out. Or you will study those more details in the next chemical class. Right. So then C. So when you observe like the wood is burning, that will give you heat or absorb heat.
Okay, sorry.
Okay, so. So that's about like the initial fundamental definition of exo or endo process. Right. So think about this CRE. Which of the following has a negative value of delta H? Negative value of delta H, which means it's exothermic process. Release heat. So release heat, that means if you're getting closer to this process, then you will feel warm. And those endothermic process, if you're getting you're getting those kind of process, and you will feel cold like what we saw on one slide. Which of the following has a negative value of delta H? Which one will release heat? Which process will release heat?
Is it E?
All of the above have positive delta H. I think one process, as I can see, it will release the heat.
A.
Hey, so that's the you probably just but that's like the first time. So that's you probably forget about those what we studied before. Right. So then the next few sections is about how to measure and calculate the delta H. But then I said delta H become very important quantity. Okay? Because if you can measure, calculate what is your delta H, and you can predict how much heat you can produce. If someone say you give me a certain amount of heat, and then you can have the chemical reaction, you can figure out how much material do you need. So that means this enthalpy change. So enthalpy change, and as we saw in the last slide, we call that delta H, is X-tensile property. What that means is those X-tensile property or those kind of property, it depends on how much you have, or depend on the amount. Alright, so that's common sense. The more resin you use, the larger the enthalpy change. You agree? Right? Like the combustion of gasoline and the exothermic reaction release heat. If you want to see that release more heat, more gasoline, right? Right. Now convention. So by convention, we calculate the enthalpy change for the number of moles of reactant in the chemical reaction as reagent. Right? Right. So when you have a chemical reaction like the reagent that gives you with balance, okay? And usually you will have those simple format, okay? Which means you don't have those common numbers in the coefficient. Right. So for example, for the combustion of propene like octane, right? So those kind of chemicals, right? And the chemical reaction gives you, let's say the simplest one that the balance is 1 of this propene plus 5 oxygen molecular O2 gas and produce 3 CO2 plus also produce same times 4 H2O. And then the information, every information is very important. So if I tell you this chemical reaction has this amount of energy, as what we saw here, that means it for this reaction as written. As written. Precisely, everything is precise. So that means for this reaction called delta H, because delta H is a negative number, which means it's an exothermic process of release heat. Now release how much heat? Release like 2044 kilojoules of heat from how much? From how much what? From as a reaction written. Which means from those one here, not one molecule by convention. Okay? From 1 mole of propane, okay, react exactly. That means all the 1 mole of C3H8 is totally gone. Then take it with it 5 mole of O2, not 6 mole, not 4 mole, precisely just 5 mole of O2 in gas, and also propane is also in gas. Then produce. So that's the initial state. Final state, which means produce something. Produce how much? Produce what? Produce 3 mole of CO2 in gas and 4 mole of water in gas. So therefore, you will have you will see our like those friend again. So what we used before is the so-called equation of converting fractions. So you can write this number with any of those coefficients. So here you have 1 mole C3H8. You can write this over negative 144 kilojoule, or vice versa, I can write 44 kilojoule over 1 mole C3H8. What do we call those? Converting fractions. It's very important. Remember converting fractions since like the first chapter? So therefore, if I have some information and if I tell you we want how much heat, if I want like 5,000 heat, and I use this information, you can figure out how much more of propane how much gram of propane do you need? You figure out what of those fractions you're going to use. On the other hand, if I tell you I have like 3 kilograms of propane, and I want to figure out if I totally use that 3 kilograms of propane according to this equation written, how much heat theoretically you can produce. Right? So then some of the people, the environmentalists, and they said, okay, you want to produce 5,000 of heat, kilojoule of heat. And then I want you to tell me how much CO2 you will produce. Well, I worry about the global warming. So similar equation. So if you have this equation, you can write like 3 mole of CO2 gas that are equivalent to this amount of kilojoules. Right? So therefore, if you said you want to produce like 5,000 kilojoule of heat, and you time this number, time this fraction here, this fraction I get from this number, is very similar as these two fractions I get. You can get any fraction between any of those chemical written in the equation. Right? Right. So that is why it's important to have this information in the so-called entropy or the delta H. So what are the so we can write here like 2 fractions, depending on which one you want to use. Or you can write for O2, you have only have 4 chemicals here. You can write this number, you can pair this number with propane, what do we have here? And the number for propane is 1 because the coefficient here is 1. And you can pair this number with O2. If you pair with O2, because O2 has the coefficient of 5, so therefore you have this 5 more. Right? I think you get it, right? And let us say this is exactly what we talk about. You have this equation again, so you saw this equation before, right? And so you have this LP. LP is standing for liquid propane. Okay, so LP equals liquid propane. So that is about this guy. Right. I think that's what this book gives to you. And if I give to you, I will probably give you a little different information. But liquid propane, assuming when you use it, that already become gas. So therefore you can. So even though that liquid propane, don't treat that literally as liquid, right? Understand? So you have the liquid propane. That means you buy that as a liquid, but when you use it in the burner, that becomes gas. So therefore, you don't have to worry about the state here down the mesh. Right. So you want to find the information about heat, and then give you information about propane. So therefore, it's very straightforward. You want to find out the equation between this number and propane. Understand? Right. So as we saw from the last slide, from these 2 numbers I circled, I will get 2 fractions. I will get 1 more C3H8 gas over 2044 kilojoules, or 1924 kilojoules over 1 mole of C3H8 gas. So we identify we are going to use these 2 because, as I said, it's very straightforward, makes sense, and give the information about the heat and give the information about propane. So you don't want to find out those fraction between the CO2, water, or O2. Now the other information given to you is this amount of kilogram of propane. Right? and you want to find out the heat, right? So therefore, you want to somehow finally have those heat as your final unit. You're going to use that one, your heat will come out somewhere. You have other heat. Right? So therefore, use some number like this. Right? So we decide use this one. Now obviously use this one. You want to get this amount of kilojoule. So right now you still have this mole of 1 mole of propane at the bottom, right? So therefore you have to find out the mole of propane to cancel out this out. But this number negative 2044 is only for 1 mole of propane, assuming we have enough those O2 to make the reaction complete. Obviously that is true. Right. So next, you can starting from 13.2 like kilogram of C3H8. Let me just assume that is also gas. Right. So then you have to convert into those moles. So obviously right now is kilogram, and I think you don't make those mistakes, right? So I will just do like one step, do a few steps of those conversions of C3H8. Even do very nice diagram, including all those units. And so you will change the so kilogram propane gas come out. So right now we'll have how much propane, how much gram propane gas. So if you want to think about it, use this number, get a kilojoule. So as I said, you want to cancel out this mole. So therefore you have to find a number of mole and multiply into this fraction and cancel out this mole. So we get the gram, and next step is what? Use molar mass, right? Molar mass. So let's say here will be molar mass of C3H8G, even though that doesn't matter with gas is liquid. And so let's say molar mass of propane. There will be 3 times 12.01 plus 8 times 1.01, and you get 44.11 gram C3H8 gas, right? And then 1 more C3H8 gas. Any questions? Okay, now you see the kind out, see the gram propane kind out. Right, so that's right here. What do we get? So we have 13.2 times 1,000, then divided by 44.11, and we get 299.25 more of C3H8 gas. Am I right? Right. What do we do next? What do we do next?
Use that fraction
Use which fraction?
or the circle.
Use this fraction, right? Because this is our question is calculate the heat in kilojoule. Right? So right now you have the mole, and if you multiply this number by this fraction and then circle, and right. So let's see if I give it some of this. What do you think? 299.25 more C3H8 gas. So what comes out? Let's see this more, and more comes out. What else comes out? The C3H8. Very good. You have to see those like the the water comes out, and more comes out, and more of what? More of C3H8 gas, right? Right. So you just have this number and then that number, which is negative, times 2044. That's negative 611,670 kilojoules. Right, so again, those will be the scientific notation to solve the problem of SF, because this number has 3 SF, right? We need 3 SF in this number, counting 1, 2, and 3. So that will be 3 SF. So right now our point is here. Our decimal point is here. So you have to use scientific notation and move it into a number 1, 2, 3, 4, and 5. Alright? So you get negative 6.1 and 2. 10 times, because we move like 5 times, so 45. And then that is a kilojoule. Alright, so that is how we use those information. Okay? So right now I have those kind of examples, so I give you this delta H, okay, for the reaction and the pretend. Now, after we study how to use that, so next few sessions, and we are spending more time on like how to get those numbers. So a different way to get that number, right? But as we know, this delta H, as what we saw before. So this delta H equals that QP, right? So therefore, you can measure, use those couple calorimeters, measure the temperature change, right? And we have other ways to calculate. You can use the sort of the Hess's law. And that's why you have some of those very common chemical reactions, and you just put them. So every chemical reaction can have those delta H. You put them in the table, then. So then we can just do the calculation. Right, so here, I think the next CRE or examples is okay, this concept, probably pretty soon we'll see some of those very similar calculations. So this conceptual problem is about the enthalpy. Okay. What we call enthalpy is H. Right? Enthalpy is H. And enthalpy is H, and H is a state function, so therefore you can have those delta H, and delta H, and delta H. I think all these 3 statements is about delta H. I think delta H is very, very important. Like delta H and delta E, right? Are important because you cannot know like those H like absolute value, but you can find out their change. You have time to read all the three choice A, B, C. Okay, what do you think? They are all true. Okay. That's good concept.
Which is the answer?
E. Right. Now this is the one that I said you will see some of those calculations, right? So this calculation is very similar as the example. What information given to you is the equation, right? What else given to you? how about a gram of something, right? How about a gram of what? Of ammonia? Okay. Okay, so what do we find out? E? How did you find out the E?
You take 115 divided by 1 mass,
Mm-hmm.
divided by 4 times 96.
The divide by 4 that come from that those kind of conversion fraction we talk about. Right, very good. So the answer is E, right? Right. So I think what most of you like find out is starting from 195 gram NH3. You said that you need to divide by the molar mass, right? So this is 1 per NH3. So I omitted the state for the conversion of molar mass, right? And this is 17.04 G NH3. Everybody get that? So this fraction is from the molar mass. Right. So then you said that you're going to divide by 4, then multiply by negative 906 kilojoule, and that comes from 4 more of NH3, and that is from the delta H reaction from the given delta H reaction or from the delta H reaction given, right? So for this chemical reaction, you will see those many times. So I will give you a chemical reaction equation like that, and then followed by a delta H. Actually, those kind of chemical reaction has a special name. We call them like the thermal chemical reaction. So once you have a delta H, follow the chemical reaction. So this is the so-called thermal chemical reaction equation. Alright, so I think that's very similar as what we did for the example. If you want to keep this kind of we said 3SF, right? Why 3SF? Because we're starting from this guy, right? This guy has 3SF. The only way to show the information right is have this kind of scientific notation. All right. Any questions? Alright, so this question actually have 2 questions. You need to find out the mass of butane and also the mass of CO2. Right. I did not want to confuse too much, so therefore all those answers are positive. And if you want to start starting the question right, also pay attention to the sign. Yeah? So even though for this problem you can get away by even get a negative sign, but all those choices here are positive. So starting from something that's right, I tell you produce heat. Produce heat. You want to produce those amount of heat, that means those heat are released from the chemical reaction, right? So therefore, that 2.5 times 10 to the positive 3 kilojoule is probably a negative number. So you're starting from that as a negative number, and you will know for sure you will get something positive. It's a little different than the last CRE. Last CRE is give you gram, you want to get a kilojoule, right? Now here you just do the opposite. You are given the kilojoule and you want to get the grams. You still want to find that conversion fraction from this number and the coefficient. It's a little tedious. What did you find out? Find out yet? Is it okay?
I'm reading the question.
Okay. What did you find out? At a D? Yeah, I think that seems to make sense. At a D, right? So if you start like with positive 2.5 times 10 to the positive 3, you might get those numbers like negative or something. But if you start from that at negative, then the negative will come out. Yeah. Why you start with negative? Because the question tells you you produce the heat, right? Yeah. So that's what I want to say. You can either see that produce heat or exothermic. Okay, so what do we get? We have D. Obviously, the converting ratio or the converting fraction you want to use is this negative 658 kilojoule, and then with like the CO2 for one program, right? The other one should be the converting fraction with the built-in. You know which one is the built-in, right? Which one is the built-in? The C4H10. All right. Any question? Anyone need like help? Some step like little confusing?
How do you solve for the CO2?
CO2. Good question. See, we have the CO2. No matter it's a product or the reactant, you just find that like those ratios, right? Right. For this problem, you want to find out because you want to find the mass. Mass is connecting to mole. So you probably want to use this 4 mole of CO2 over negative 2658 kilojoule. Right? You get 4 from this coefficient. Right? So you starting from negative 2.5 times 10 to the positive 3 kilojoule. So this number, as you know, that you have the negative because it produce or release heat. So produce or release heat, which means our chemical reaction is an exothermic process. So you can think about that. So your delta H will be a negative number, even though give you the heat is some positive number. And you can also think about use those sign convention as what we studied in the first section, right? So in the first section, I will give some numbers for the heat, give some number for the work, and then you decide should you use a positive number or negative number, depending on whether the heat is released or absorbed, right? So release heat is negative sign. Right. So then negative comes out, the kilojoule comes out, so you get how much more of the CO2. Right? And then next, because all those answers is in gram, right? So we will use 1 mole CO2. And for here, because it's about mass, So mass in like a gas state or in liquid state have the same mass. So you don't worry about those that. All right. So what is the molar mass of CO2? 44.01, right? So more CO2 come out, so let's see what we get. I think that's probably 166, right? 2500 divided by 2658 times 44.01. And right, I get -65.57 and so on. So we're on to like -66. All right. Right. Any other questions? Right, so now let's talk about how we measure that. So we have one slide, we talk about just principally, if you want to measure the delta H, right, you measure the Q. Right, so delta, this one right here, delta H reactions that equals Q reactions. But usually the Q reaction is not easy to measure. Q reactions add those kind of process. Right. So you measure the opposites, measure the other parts. So there's a heat exchange between the chemical reaction and the calorimeters. So let's see this. So as an image side, I think you get it now. So for those kind of calorimeters, so even though it looks like zero, but there's a lot of space and room can interchange the gas and air. Therefore, it's really open to the atmosphere, even though not that much open to the heat. The calorimeter is often nested, so that's you can see. And I think that's one confusion is, or sometimes you're not really confused, but you will forget, is this equation here, make sure that's opposite, right? Right. So let's say this usually is what you need, or what it gives you, right? And that's usually what you measure. Right. It's easy to measure the temperature change of the solution. You can see the thermometer is in the solution. Right? So even though in this kind of process, as I said before, there's not only the energy change between these two, between the reaction and the solutions, there's also material change. So you take some of those chemical reactions, right? Let's say like 1 gram of some, maybe some of those salt, maybe 1 gram of sodium hydroxide, and then like maybe 50 milliliters of HCl. So then you're obviously that your solution, that 50 ml, and it has water. That is really our other part, our solution, right? But when you are thinking about all those chemicals together with the water, that become the solution, that become the surrounding. Therefore, there is kind of a mingle, a mix of the environment, of the surrounding with the cysteine. So some part of that cysteine become the surroundings. That is definitely typical. That's not really some mistake. You can think about that some of those open cysteine. So obviously here, and what you can use is one of the two equations. You can either use this one or use that one. typically in this kind of calorimeters, you can use the first one, because you can measure how much, as I said, 50 ml of HCl, so therefore you can measure how much gram of those solution you use. Okay? It is very easy, very straightforward. So therefore the equation typically you're going to use is the specific heat capacity. Right? So then once you have that chemical reaction, okay? Once you have that chemical reaction, and you get that from that Q solution, negative Q solution, okay? And you get that Q reaction. Okay? And so then I said most of the time for those kind of, we use this kind of equations, and that not means you cannot use this one, and if you have those information, you also use this capital C. And so now what you measure, you just see like what kind of process. If your process is a constant volume, and you always have that equation, okay? And you always have this kind of equation. You just see, you somehow measure this Q reaction. Okay? Then the Q reaction is heat, and we can give that another name. We can say that either is our delta E or our delta H. So now another details is yeah. So that's you see like usually you will see measure those delta E or delta H for whatever that gives you, right? But you can also like be more precise. So you will see like one of those few programs you want to measure those delta H, for example, is per mole. So in the first few sections, and we kind of make simple. We just use this equation and get what is delta H. And then in a few of those CRE or examples, once you get delta H, just divide by the total mole and get how much kilojoules per mole. Okay, any questions? You can do like a per gram. And what we did in that PowerPoint lab, right? So we measure those heat, use this equation, calculate, and get the Q reactions. Then we divide by gram, and then we see how much kilojoule, right, per gram. Yeah, so that's a little more precise, because otherwise you'll see that is just for that amount of kilojoule for that huge amount. But you want to be more precise, you can say per gram or per mole. So we have that equation, the magnesium solid plus HCl equals and MgCl2 equals. So that equation is balanced. Right. So in one experiment, you want to decide what is the enthalpy change for this reaction. Right? So you want to find out, pretty much you want to find that delta H reactions. Right? Find delta H reactions. So therefore, we can use what we learned. You want to find out that, so that will equals QP. Maybe use another subscript. QP reactions. You know, both of these subscripts, the P standing for constant pressure process, right? And reaction standing for reaction, so we still don't have the sign change. Right. So then, because again we need to do like a few problems, because this question asks you like to get that to get this delta H for the reaction as written. Right. And so now let's just find out from those information, just find out what is delta H for those informations. Then we go to the last part and how we convert that into the equation that is written. So then because that was we saw before is QP reactions equals, so that is because negative QP calorimeters, understand that? So because QP reactions equals negative QP calorimeters, so that's are the two parts of the universe. One part is the chemical reaction, the other part is the calorimeter. But in this particular example, your calorimeter becomes simpler. Because the calorimeter is just two cups, and then there are some of those liquid or solution in it, right? So actually your calorimeter become, you can simply call that a solution. So as I said before, you have that system and surrounding that are two templates. Template is our system and surroundings. That depends on the problem, and you identify what is your system. Your system, in this example, it will become this Mg metal. And then your surrounding. The surrounding can call that calorimeter. And calorimeter becomes simplified. Calorimeter simply become a solution. Then you will simply call that your surrounding solutions. So now let's see. So this QP calorimeter equals QP solution. So this SOLA means a solution. So why we call that a solution? Because we have the information of the temperature change of a solution. That's very clear. So now we will just continue. And so now we switch, so this will equals negative QP solution. Think about without the negative sign, just like Q, without the negative sign, or just negative sign with Q. So you have either one of those two equations you can use for the Q. Right? So which equation should we use for the Q? We will just rewrite the negative sign, and we are going to replace the Q solution by one of those two equations. So what equation you think should we use? Either one, actually. You can use the bottom one or top one, right? Even though probably just straightforward, just use that M times CS times delta T. Do you agree? Alright. So I make that notation become simpler, so I omitting all the subscripts, so I will omitting the constant pressure I also omitting that solutions. I tried one this step. So you say rewrite the negative. Do we know the mass of the solution? You understand why we just start with the solution, right? Because we are assuming our solution, our surrounding becomes solution. So this surrounding become solutions of the solution. Right? Alright, so what is the mass of the solution? 100, how do you, that's not, yeah, that's not bad. 100 gram solution, you get that from what? The information did not give you directly, is how much what? 100 milliliters, so then how you find out that it's 100 gram? Yeah. So you have 100 ml, you have that 1 gram per ml, right? So you don't see that not one. So you have 100 0.0 gram. So then put that in the bracket. So what is our COS? Did the question tell you what is our COS for the solution?
4.15.
Yeah, so that is assuming the same as water, 4.18 joules per gram per Celsius. Okay, what is our next? Temperature change. Temperature change. So let me write here. So multiply by the delta T. How do you find out the temperature change?
Final minus initial.
Okay, so our final is 32.8. Agree? What is our initial? Alright, so both of them have Celsius, so therefore we have Celsius for delta T. Right? Right. So let's see what we get. 100 times 4.18 times 32.8. That's about solution, right? Right. So you have a negative 300, that is 9.6. What our unit? Right now is joule, right? Right. So I think we are little like we have little information about this problem, but we need to get the final format. Right? Well, the question is about. So let's say this. Right now you have this called the delta H reactions. If I write that together, right? So delta H reaction equals negative 9.6 joules. But this is for like what? For this 0.158 gram of Mg metal and with enough HCl. Now the question is, you want to find out this delta H reaction. Delta H reaction as written for the equation. As written for the equation, so this equation is balanced, and the information given to you is about Mg. Right. So in few of those questions, we talk about we converting this information right now here is for this 0.158 of Mg into like per mole of Mg. In our lab, we convert into per gram. If you want to convert this information into per gram, that's easy. You have to take this number divided by that gram. Right? Right. Now, what should we convert into? Should we converting that into that, or converting that into per mole? Per how much mole? Per 1 mole? Why is that per 1 mole? Because that's the same like that. The equation has 1 mole Mg, right? If you want to convert into this equation as written, you have to think about how can you get those delta H reaction, for example, for the HCl, you have to find out per 2 moles, right? But for Mg is per mole. It's a kind of coincidence. Therefore, you divide that mole of Mg. You can find out how much mole from 0.158 gram of Mg, and then divide. You get per mole. But you want to find out per 2 mole of HCl, you just divide, find out per mole, then multiply by 2. Alright. So then you erase those. So that's again the result of our part 1. Delta H reaction equals -3, 9.6 joule. Right? This is for what? 0.158 gram of Mg. Right. So we need this delta H reaction in like what do you think? For the reaction as written, well, did not tell you whether it's kilojoule or joule. I think better probably is not kilojoule per mole of Mg. Right? So why per mole of Mg? I already try to explain why per mole of Mg, even though that's really not the question asked you directly. Right? So I said, you want to find out this delta H reactions in kilojoule. This kilojoule I put down, you can use joule, that doesn't matter. But the question is, the important point is per mole of Mg, not per gram of Mg, not per 2 mole of Mg. Why is it per 1 mole? Why is it per mole of Mg?
Because the equation gives you the moles of each.
The question asks you to get that delta H for the reaction as written. Right? Well, as written, that means as whatever those coefficients. So I think that the coefficients written in the equations, right? So what is the coefficient for Mg? Is 1. And so that's why you use that per like Mg, per 1 mole of Mg. Alright, that is what we get from the last step. And so therefore you have to convert this 1.58 gram of Mg by the molar mass of Mg. Okay, anyone I know the molar mass of Mg? 24.31 gram of Mg. So the gram Mg comes out. What do we get? 0.158 divided by 24.31. 0.006499 mole of Mg. Okay, so what do we do next?
You divide the kilojoules?
Well, we don't have the kilojoules now. We can use joule, but yeah, I think right now we have the joule, right?
So just convert it to kilojoules.
Okay, so we'll just
Divide
start
it.
from negative 3,009.6 joule. Then we say 1,000 joule is 1 kilojoule.
So about 3 kilojoules.
Yeah, so that will equals negative 3.01. Let's just make the 3SF. Then what?
Divided by 0.0065.
Okay, so we'll take a negative 3.01 kJ divided by 0.0064999, which is that much more of mg, right? Right, so that seems getting better. I was really confused. So, yes, I see you move your head like what you did before. So E cross because of what? Okay. 3.01 divided by the number -463 kJ per mole of what? Mg? I did not remember this. Now it seems very, very strange. -463. Is that right? Okay, so but the procedure is right? Well, see that question. Otherwise, I'm not familiar with. Well, we use joule. So I said use kilojoule. Because those numbers, usually those numbers are very like long numbers. So therefore, I just use. So I just probably use kilojoules. Very easier. But it's okay. Scientific notation. You can see like two if you use like the kilojoules, so this will be 10 to the positive 2, right? So now you have 10 to the positive 5, so that's definitely that's okay. That's the same. Now the question is, so you already see like two of those practices. So you have two parts. You first find out delta H for whatever will give to you, and then you divide by the those mole of gram. Then you will see like whether you should divide by the gram, you will get per gram per mole. So make sure you convert those per gram per mole into that the question asks you. Okay. Usually the question I think for this one just asks you want to get those delta H for the reaction as written. For the reaction as written, that's just 1 mole of HCl, 1 mole of everything. Understand? So again, this word sometimes kind of annoying, right? Whether that's really just annoying or not. But if you get one time you see annoying, then next time you will see not annoying anymore. So you see this as written, right? As written, that means for one this, right? One this, one that. And you can just find out the two parts. First find out delta H, and then the second part, take the delta H from the first part, divide by the mole, get per mole. Let's see too much. I think you already know how to do it. Kind of tedious. Sometimes you probably forget the sign, and sometimes you probably forget the divide by the what you get by the total moles. the total number is not asking to divide by the total number, but just see that you wanna like get the total age for the writing and reading. Oh, don't forget in the text bag. And exam one, I use you like that. That's the first part. What do you find out?
Oh, I'm just, still
Okay, not really. Just be careful. I think you missed one number. You see that what we did in the example is use that Q equals M times CS times delta T, right? Think about what is M?
That's why I got confused.
M is the mass of the solution. So now what make our solution?
Well, it's in molarity, so I don't really know what to do with it.
Yeah, so we have like two rectangles, right? We have two rectangles. So make sure you get all the material in the solution. So you have two rectangles and 80, right? So you have 80. Yeah, I think that's the one you made.
Yeah.
So make sure you have a 40 ml HCl. You also have 40 ml AgNO3. So you have the same volume and same concentration, AgNO3 HCl, the more ratio is 1 to 1. What's the answer? You want to get some number? Negative 93? Very good. You want to write out what you did? Right here. Get the marker already, some of the marker is kind of. Yeah, so you first have to figure out how much more. It's very good practice, and how much more of each reactant, right?
The total reactants, the mass of all the reactants, right?
Yeah, yeah. And so then that's one like difficult to figure out what is the mass of kind of our surrounding. And in this example is relatively easy because we have 1-to-1 ratio, and then we have the same volume, same concentration. So therefore both reactant is consumed. Right? Remember in chapter 4 we talked about those limiting reactants. And limiting reactant, excess reactant. The equation just.
Probably a fair way to do it.
So that's a good review. I think I just saw your lab report today, and for the last lab we did like the Arnhem, and I think one question, you know, that in the calculation, so you want to figure out how much more of H2SO4 you use, how much more of KOH you use. Just very similar conversions. Yeah, very good.
It's
Right, so,
probably,
yeah, you just
probably an
frame-
easier way.
yeah.
So we know that the change in H of the reaction is equal to Q of the reaction, and Q of the reaction is equal to negative Q of the solution. So you can solve for Q of the solution. You add the two volumes that we had. 80 milliliters converts to 800 grams per mass. So this is your MC, change in T. C is in the problem, change in T we subtract. And it comes out to 3,712 joules. And then we go back to this formula, we've got that. And then we wanna find the moles of HCl.
So there's still X more, right? There's still X more, because there's not per mole, and more here, you don't know how much more, right?
Right,
And the
so
other
you're
one.
solving for whatever
Yeah,
the
whatever
moles are. So you can find the moles of HCl by using our old molarity equation, where molarity equals moles over liters. And then so to solve for moles, you just change it to that, and then you end up with that. And then you come back to this, you convert it to kilojoules, which is 3.712, and then you use your moles of HCl. Measure 92.5, and then for significant figures it's 93.
I think your check already your number. How about air? What is the volume for the HCl?
So it's 40
40 ml.
milliliters.
40 milliliter into liters.
That's 0.04, isn't it?
Yeah.
Yeah.
That's okay. So I think that probably you did that in your calculator, but you did not.
Yeah.
Where does the 800 come from?
So you have 40 milliliters of one solution, 40 milliliters of the other, and you need the entire volume. So you add them together, and then 10 milliliters is equal to 1 gram.
Oh, okay.
Is your liters correct? Because it's 40 milliliters, shouldn't that be 0.04?
Yeah, that was wrong.
Yeah, that's what I said. But she don't know that. Any question? I think that's, yeah, so here, the same to this, 0.0. I think that the important part is, you don't forget, once you mix these two solutions, right? One is 40 ml that HCl, and the other one is 40 ml the AgM3. And you mix them together, obviously, all in the calorimeter. And then heat will not only go to 40, it will go to all the 80s. Right? So therefore, 80 become the 80 ml really become the surrounding. Yeah, so each time you do the calculation like that, so make sure, I think what she did is cover cell identify very good. Just make sure you identify what is your total, the chemical reaction in one part, right? So then what is your other part? The other part you have, in last CRE we have the Mg. Mg we ignore or neglect because Mg is 0.158 gram. And put together, we said that produce 100 ml of solutions. So not like we kind of neglect or ignore, but not really. I mean, in the calculation, we still consider that 0.158 gram of Mg is in the solution. So therefore, I think you probably get that habit. You see that you only take that 100 ml, and here you have 40, another 40, and so that you can like put them together. Okay, any questions or comments? Alright, so you get this one. Okay, so that's what I was thinking about. If I do it, I will do it here. So you already on the board. Right. Now we have some of those way to measure, okay? And so then some people did some of those measurement or do some calculation like what Megan did here. And so then they will put those numbers in a table, and you can see in your textbook in that appendix C or something that apply through those numbers. Even though those numbers is for some of those special chemical reactions, but that means you have those chemical reactions, and you can use those numbers to do some calculations. Now, before we use those numbers to do the calculation, we have to study some of those few of those very important relation between the delta H and the reaction equation written. Right. So one relation is when the chemical reaction is multiplied by a factor, multiply the same as divide, right? I mean same as divide, and you will do the same for the delta H. Let's see one example. If I have this carbon S, which means carbon solid, plus O2 gas, a typical combustion reaction, and produce CO2 gas, and tell you for this reaction as written, and you have delta H equals -393.5 kilojoules as written again. What do we mean by as written? So this amount of kilojoule that was released from how much carbon? From how much O2? From how much carbon? 1 mole carbon. From how much O2? 1 mole of O2. Then produce how much CO2? 1 mole of CO2. And even though the gas probably gas or solid is also important. So the chemical reaction is written like this. Now what this first paragraph tell you, and if you multiply that equation, for example by 2, even though after you multiply that become 2 and 2 and 2, is not the usual way you write a chemical equation. The usual way you write the chemical equation is you balance the equation, and then all those coefficients is integer, and also the simplest ratio. Even though pretty soon you will see some of those chemical reactions, you don't have to keep everything as an integer, as long as you keep that one product as integer as 1, right? So now this is not the common way, but just to tell you those kind of what this means. If you multiply this equation by some number, in this example you multiply every coefficient by 2, and you get this new equation. Now this new equation will have delta H new, because delta H or H are the so-called extensive property. So therefore, if you multiply the equation by 2, that means you have twice all those material, and your delta H will be twice. So delta H initially negative, you still have negative, but you have twice that amount negative. And so that is one property. The second property is if you reverse the reaction, I mean if you rewrite the equation as reverse, and you're probably very familiar with those kind of different way of writing chemical reaction equations. So for that last example, we have this CO2 as a product, and obviously we can rewrite the CO2 on the left side as reactants. So if you do that, And you can also multiply by number, but you do like one thing at one time. Okay? So if you simply reverse that, if you simply reverse the CO2 and on the left side, and then you set the carbon and O on the right side, so compare this one with the first one, what we did is reverse the equation. So therefore, your delta H has the same magnitude, but the sign is inverse. So I will tell you like one last operation, one last property is difficult to understand. So take some time to read that, which tell you is the so-called Hess's law. That tell you if you have a chemical reaction that can be written as the sum of a few steps, and then your delta H will be the sum of that few steps in your summation. And in this diagram, okay, you will see this reaction from A plus 2B produces 2D. So that is one reaction. And there are two other reactions. One reaction is A plus 2D produces C, and C produces 2D. And you already have that level report for your R-level lab. And I think if you do that level report and you did some of those pre-level questions, you know how to add in equations. If you take this equation 1 for that A plus 2B produces C, and equation 2 is C produces 2D. So adding that two together, you will get this equation 3, which means A plus 2B produces D. And then when you do the delta H, you will have the delta H3, so this is for this reaction, equals delta H1 for that reaction plus delta H2 for that reaction. So when we come back, thirdly, we will finish this chapter and do the lab, which is about FE, the RNA in the cereal. So this is the lab menu. Right now, not negative. So this right now here is a solution.
Okay.
So you just keep like positive, 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 whatever you get. Then you see this is one important equation is identified, and this is also another one important equation identified.
Okay, so then once you get down to here, that's when it became negative.
Yeah. So that's if that is positive, that will become negative.
Okay. And that's where you would plug into this equation here.
Yeah.
Now you need the moles of HCl. So you have a molarity.
You have So review those. Those are very important. You have to know like how to. I think you did pretty good on that report. You see the. So you have that molarity given.
Those are the liters. Okay. You're given the molarity.
Yeah, that's the 0.1. That's the kind of end.
Which would be this.
And that number was she's right. She what she means is that she just knows that she had that 40 on 0 ml, right?
Yeah.
And you know, I mean,
Times
she
1,000.
knows, she just kind of, so you get 0.0400 L,
Okay.
and then you'll get 0.00, right? 0.0400 more.
Okay.
Yeah.
And that's when you divide that. by
That
point-
I divide by that.
Wait, should it just be point? Zero?
No, see,
Oh, there is an extra zero.
yeah, so that's 0.004.
Okay. That's a good answer. Cool. Thank you.
Do you actually post the videos on?
Yeah, I put on YouTube.
Are you put it on YouTube?
Yeah.
Do you have your own channel and everything?
I have my channel. What I try to do is, I saw some of you probably like, watch it, and so you can just some of those you can review it. You can use the class.
Cool.
And mainly for
What's
my
the YouTube channel name?
you just search it like John Wayne chemistry, and you will find it.
Oh, nice.
So I think you just search like John Wayne. If you want, you can see like general chemistry.
Oh, cool.
So I have right now I have the channel. I have also a playlist.
A what?
A play.
Oh, playlist. I think that's okay.
I think yes. I think I just put those there, and my main problem is so I want like to see like how the level goes. So I want like see like what really is right and the way cheating depending on
Oh, so you watch it after and you
yeah.
critique yourself on it?
Yeah.
That's cool. Alright, well thank you. Have a good night.
We do.